Yeah, so getting started a bit late today. Sorry about that. I am moving and I have set up my little mini station here at my parents' place, and couldn't find any of the cords, but now I'm rolling. So promise next time I shall be on time. This week I wanted to look at this causal imitation learning with unobserved confounders, and with some of the students I've been teaching. They've been really interested in the relationship that causal modeling has with reinforcement learning. And I so yeah, I've been encouraged to go dive deeper into this connection. Elias Barenboim's group over at Columbia has been exploring this relationship between um, reinforcement learning more broadly, things loosely related to Markov decision processes and agent models, and how they tie into causality. So this is a paper that was presented at this year's NeurIPS, and I didn't get a chance to go over it yet, so I'm going to just do it now. I have the paper actually loaded up here in my browser. So great, we can just dive in here. Okay, what's the abstract say? So one of the common ways children learn is by mimicking adults. Imitation learning focuses on learning policies with suitable performance from demonstrations generated by an expert with an unspecified performance measure and unobserved reward signal. Popular methods for imitation learning start by either directly mimicking the behavior policy of an expert, behavior cloning, or by learning a reward function that prioritizes observed expert trajectories, inverse reinforcement learning. However, these methods rely on the assumption that covariates used by the expert to determine his or her actions are fully observed. So let's just kind of hash that. So we have this thing now. Imitation learning is this way of learning policies, things that actions that policy is a mechanism for suggesting actions that are going to optimize some kind of reward, and we're going to be learning policies based on demonstrations from experts. There's some unspecified performance measure, so the expert is optimizing some kind of utility that we're not aware of, and unobserved reward signal. Actually, I'm not entirely clear what the difference between performance measure and reward signal mean. Maybe performance measure in terms of how well you're learning from the expert. Popular methods for imitation learning start by either directly mimicking the behavior policy of an expert. This is behavior cloning. Or by learning a reward function that prioritizes observed expert trajectories. Inverse reinforcement learning. Okay, so we're looking at two things. One is mimicry, and one is trying to learn what the reward function is that's going to optimize the thing that the person is doing. So this is looking at an agent, presumably an expert agent, and trying to figure out, okay, well, they're doing this thing, and we assume that they're doing it to optimize some kind of ultimate reward. And so what might that reward function be? However, these methods rely on the assumption that covariates used by the expert to determine his or her actions are fully observed. So in other words, that we don't have any kind of unobserved confounders that are possibly affecting both the actions and the rewards of that expert. I wonder if this fully observed by whom? Is it the observer or the expert? In this paper, we relax this assumption and study imitation learning when sensory inputs of the learner and the expert differ. First, we provide a non-parametric graphical criterion that is complete, both necessary and sufficient, for determining the feasibility of imitation from the combinations of demonstration data and qualitative assumptions about the underlying environment. All right, so I assume that qualitative assumptions are going to be this causal graph, and then we'll get a graphical criterion based on that causal graph that will be both necessary and sufficient to determine if it's even possible to successfully imitate the expert. right? These qualitative assumptions represented in the form of a causal model. We then show that when such a criterion does hold, imitation could still be feasible by exploiting. Does not hold. Okay, it could still be feasible by exploiting quantitative knowledge of the expert trajectory. So okay, so what we're going to say here. So this first bit here is going to say that we're going to have a way of telling whether or not imitation learning is even going to work when there are when the things that are being seen by the learner and the expert differ. And if it does not work, then we have some kind of remedy. That remedy is going to be imitation could still be feasible by exploiting quantitative knowledge of the expert trajectories. I guess we'll have to figure out what quantitative knowledge means here. Finally, we develop an efficient procedure for learning the imitation policy from expert trajectories. Okay. Efficient. That doesn't sound so exciting. It'd be nice to see if it was like a procedure that was strictly better than kind of normal imitation learning policy methods. But I guess what we're saying here is that if the learner and the expert observe are different, then you can't, assuming some kind of causal model representation of the environment, then efficiency doesn't come into play because those traditional procedures won't even work. Let's see.
Hey everyone, my name is Zhunzhe Zhang. Today I'm going to present our work, Causal Imitation Learning with Observed Confounders. This is a collaborative work with Daniel Kummer and Professor Baron Bowen. Imitation learning is a learning paradigm where an agent or learner tries to obtain a policy from demonstrations of an expert so that they can achieve the expert performance. The challenge here is that reward signal is often unobserved. Most of imitation learning algorithms assume that the expert and the learners share the same state action space. These algorithms include behavior cloning and inverse reinforcement learning.
I'm trying to think.
The challenge here is that reward signal is often unobserved.
Sorry. So I'm trying to actually think of an example where the thing that the action space that's observed by the expert and the learner are different. I mean, one is tempted to go to toy examples, like say for example, a game, right? But in most of those game examples, we both assume that both the expert and the learner see the same thing. So it'd be nice to think of a really kind of simple yet practical example where the expert and the learner are seeing different things. Imagine trying to learn from some expert who's performing a job, but that expert has access to proprietary information when making their decisions. But it'd be nice if you could just boil that down into some kind of game. Another example could be, say, you're watching somebody play poker, and you are a member of the audience, so you see everybody's hand. So you have more information, but of course, the expert who's playing the game only sees their hand. So in that case, see, that's the same state action space. It's just that they have partial information about those states. So
algorithms include behavior cloning and inverse reinforcement learning. Our goal in this paper is to generalize such assumption. We will perform successful imitation learning when some input variables of the demonstrator's policies are unobserved. Here, we show a graphical representation of the problem setting. we model the underlying environment as a structural causal model. And in such an environment, an expert agent decides value of the action X through a behavior policy Fx, and in return receive a reward Y. We also have a learner agent that intervenes on the same action X, but through a different stochastic policy, pi X given Z. Here, Z is a set of covariance variables. The learner does not observe the reward Y, but only a set of variables O. Therefore, we call such a joint distribution P of O as an observational distribution.
Let's look at this. Say, all right, so can I get subtitles on this? Oh, they got those weird Google subtitles. All right, so we got this action and policy, which gives us action that affects the environment. What do we have here? So we have these structural causal models. So we have some exogenous and endogenous variables. So what a structural causal model is? Just a special kind of causal model. It's the kind that Barenboim, who's a student of Judea Pearl, works on, and it's a generative model, so it's very much within the scope of these streams. But let's see here. So we have two types of variables in the model: an exogenous and endogenous ones. These will be functional assignments that map, that set the values of the endogenous variables, and some kind of underlying distribution on the exogenous variables. So we can talk about what that is later. But anyway, it's just a causal model with a DAG, and this determines what the reward is. So reward here is indicated by Y. We observe both V. Oh, okay, maybe V and U. Maybe V and U are not exogenous and endogenous. Maybe like there's some kind of set of these. We're splitting our variables into sets that the expert observes, but maybe not. Okay, no, that's not true. See so even U they observe. So I don't. Okay, so maybe U here are some confounders. V not in Y, so we don't see the reward, and we only see some of the we only see some O's. So yeah, I'm not sure what this V and U means here. We see some observed variables here, and what is this bit here? So we have some kind of policy that generates samples of X given Z, and what is Z? Don't see that here either. Okay, so
the goal of the learner is to find the imitating policy pi from the observational distribution P of O such that its performance, the learner's performance, expected value of Y given to pi is equal to the expert's performance, expected value of Y.
I gotta go back.
Observe the reward Y. The value of the action X through a behavior policy Fx, and in return receive a reward Y. We also have a learner agent that intervenes on the same action X, but through a different stochastic policy, pi X given Z. Here, Z is a set of.
So the learner is actually doing stuff, and they're doing it through some kind of stochastic policy. So this is a deterministic policy that's just going to say, all right, just do the action that optimizes the thing. This is a stochastic policy. Why is it stochastic? I don't know.
Of covariance variables. The learner does not observe the reward Y, but only a set of variables O. Therefore, we call such a joint distribution P of O.
He said something about O.
Z is a set of covariance variables.
Okay, Z is a set of, I think he said covariates. So things that are happening alongside X there.
The learner does not observe the reward Y, but only a set of variables O.
Okay.
Therefore, we call such a joint distribution P of O as an observational distribution. The goal of the learner is to find the imitating policy pi from the observational distribution P of O such that its performance, the learner's performance, expected value of y given to pi is equal to the expert's performance, expected value of y.
Okay, so I think we're learning some kind of stochastic policy. It's going to say, in other words, that it's a distribution that samples actions and we want to so we want to find this so that we're the expected value over m, which is not clear what m is, of y given do whatever the policy tells you to do is equal to. See, this notation is confusing. This makes it look like the outcome y is independent of the actual policy. I think what this means is that that maybe there shouldn't be an m here. Like this should be expected y over maybe O. Given observations O, not including y. Yeah, and O doesn't even show up here. So I kind of get it. This notation's a bit janky, but we're trying to say that we want to get this. We want to optimize this policy so that we're getting some expected value of y, which of course we don't observe. That is equivalent to the performance of the expert.
The goal of the learner is to find the imitating policy pi from the observational distribution P of O such that its performance, the learner's performance, expected value of y given to pi is equal to the expert's performance, expected value of y. We now show a simple example of imitation learning from drone footage, aerial footage of human driving in the highway. In particular, we'll consider a learning scenario where there's a car in front of the demonstrator car.
Front car.
Here, x represents the acceleration of the demonstrator car, and y is a reward function measuring the performance of the driver, that is, the demonstrator or the learner driver. And z is a set of covariance variable that summarize the velocity and the locations of both cars. And in this case, the demonstrator decides whether to accelerate or decelerate based on values of covariance z and the tail light L of the front car. Since the drone footage does not record the tail light information, the observational distribution from learner's perspective is summarized as a joint distribution P of x, z. And the learner decides values of x, accelerate or decelerate, based only on the covariance information z. That is, the learner's policy is of the form pi x given z.
Okay, all right. Oh, shoot. Let's see if I can capture what's going on here. So we got a front car. I suppose this is the expert. So let's imagine we had a human who is driving a car, say around some kind of training track, and behind it is a self-driving car, and that self-driving car is trying to mimic the human's behavior. So we might say that, all right, well, if we just kind of have this self-driving car kind of learn at least when to speed up and when to slow down. That kind of makes sense to me, I suppose. One of my students was really kind of complaining recently. He's a reinforcement learning researcher, and he was talking about how all these causal modeling papers, as they pertain to reinforcement learning, always use these simple 3 or 4 node examples, which if you're kind of used to working within the complexity of reinforcement learning, You just kind of look at that in bulk. But this actually seems perhaps a interesting motivating example. Let me think. So the x here is the acceleration of the expert car, and y is the driving performance. We don't see what that is. At least the observer doesn't see what it is. Z is velocity and locations of both cars. And this bi-directed edge here implies that there's some kind of confounding variable that affects both the location of one or more cars and the driver's performance. What that might be, maybe, I don't know, the location. Velocity and location, I don't know, maybe the driver's not feeling well or something, I don't know. The expert's not feeling well. Light, L is the light of the front car, tail light of the front car. Why would that be latent? You'd think that the learner would see the tail light just fine. P of X and Z is the observed variables in the system, and pi is right, the actions that we can do. So actions is accelerates, not accelerate, and based on Z. So given velocity of locations of both cards, the learner is going to decide whether or not to accelerate or slow down, I suppose.
C is of the form pi x given Z. We next show that in this simple environment, naive imitation does not always lead to optimal imitation performance. Consider a simple SCM as follows. The reward y is given by x exclusive or L exclusive or Z. Naive imitation does not always lead to optimal imitation performance.
Naive imitation.
Consider a simple SCM as follows. The reward y is given by x exclusive or L exclusive or Z. X is given by not L exclusive or Z. And values of D and L are drawn over a binary domain, 0 and 1. In this environment,
okay, what he's doing here is he's showing an example of a causal model. So this is a structural causal model because what we have is we got y, x, and z, and these are determined deterministically by these functions here. So we have, so let's start with z. So z and L are drawn uniformly over 0, 1, although L here is apparently caused by z, so that doesn't seem to correspond with this graph. X here is not L or Z. What is L again? I've already forgotten. Z is position. L is the tail light. So the tail light is off, or see, I mean, I wasn't thinking of these as binary variables. Y is X or L or Z. So okay, so something they're about to explain why this makes imitation learning hard, or naive imitation.
We find that the demonstrator is indeed optimal. That is, expected value y is equal to 1. The imitation applying behavior cloning gives the policy pi equal to conditional distribution p of x given z. To our surprise, the expected value associated with the policy obtained from behavior cloning gives a performance of 0.5, which is far from the optimal expert performance, which is 1. This simple example shows that naive behavior cloning could lead to suboptimal performance even when the expert is optimal and the cloning is perfect.
So I don't really understand this example, but what they've done here is they've shown some example where if we just do behavior cloning without any of this causal stuff, then we can get to a suboptimal policy. I don't have an intuition for how much of an edge case this counterexample is, but there we have it. We see that they've made the case for why you need to take a causal approach to this imitation learning problem.
This means that behavior cloning does not guarantee the successful imitation given the observational distribution alone. To circumvent such issues, our solution is to explore causal relationships of the underlying environment.
What I'm doing here is so this is a live stream that I'm trying to get a regular cadence for weekly on Friday at 11 a.m. Eastern time, and I'll be looking at reading papers. We'll be reading papers largely in the area of causal and probabilistic modeling. So this is actually pretty nice, being able to kind of just go through this inbox of NeurIPS papers that I have meant to look at. It's obviously these recorded oral presentations are meant to be a lot more digestible than the papers themselves. So I actually kind of like this format. So if you have any questions, just ask in the chat window.
Let's revisit our problem setting. We'll represent the causal knowledge of the environment using a causal diagram. A causal diagram, G, is a directed acyclic graph where nodes represent variables and
so let's just refresh ourselves on this graph. So we're trying to do imitation learning. We have a car that's following an imitator car is following an expert car. The expert car X is the expert car is slowing or accelerating. X is the follower car, the observer car, slowing or accelerating. This leads to some kind of performance which the observer doesn't see. There is some kind of this Z here is the position and velocity of both cars that is observed. This is whether or not the tail light is on of the expert car. Don't really understand what that's doing there. And there's some kind of confounding between Z and Y. There's some kind of latent variables that are affecting both Z and Y that are unknown to the observer. And we just showed an example for counterexample for why behavior cloning, which is just trying to mimic the behavior of the expert, isn't going to work under certain types of certain ways of parameterizing this model here could lead to suboptimal results in behavior cloning. So we're going to see, I guess, how we do this with imitation learning.
Arrows represent functional relationships among them. We assume that the learner agent has access to a causal diagram G. And the task now is to find the imitating policy pi from the combination of the observational distribution P of O and the causal diagram G. Before we proceed, I would like to briefly talk about the big picture and the main contributions of this paper. So far, we have modeled the imitation learning through causal semantics. And we also show that behavior cloning does not always lead to successful imitation. A natural question at this point is whether or when imitation could work, in particular using the approach of behavior cloning. We'll answer this question by providing graphical conditions under which behavior cloning could work. And if that is not the case, we also introduce a novel family of imitation methods that can lead to successful imitation even when behavior cloning is probably insufficient.
I don't even know. During NeurIPS, I kept
the first condition is called imitation by backdoor. The theorem states the expert performance, P of Y, is imitable if there exists a set of nodes Z prime satisfy the backdoor criteria. That is, Z prime is a subset of original covariance set Z and
Missing this. I
nodes
gotta
x
go
and
back over
y,
that.
or passes between node x and behavior cloning could work. And if that is not the case, we also introduce a novel family of imitation methods that can lead to successful imitation even when behavior cloning is probably insufficient. The first condition is called
That was
imitation by
probably important.
backdoor.
I just want to look at that one more
In
time.
conditions, graphical
So we want to know
conditions
when
under
behavior
which
cleaning
behavior
works.
methods that
We
can
want to
lead to
know.
successful imitation.
We want to know a novel family of imitation methods that can lead to successful imitation, even when behavior cloning is provably inefficient. Okay, so they're going to give us some new methods. So great, that's a contribution. And was that it? Okay.
Even when behavior cloning is probably insufficient. The first condition is called imitation by backdoor. The theorem states the expert performance P of y is imitable if there exists a set of nodes Z prime satisfy the backdoor criteria. That is,
all right, so that we have a backdoor from X to Y through Z. So this would be the backdoor here. And we observe Z, so presumably we can close the backdoor by conditioning on Z. So what did I write here? Z, backdoor criterion, Z prime in Z, which I'm not sure what Z is, and X is independent of Y given Z prime. So that would be true, well, in a graph that removes edges from X, right? So if we remove this edge, then we would have this X, Z, Y path, and if we conditioned on Z, that would block influence from X to Y. Outgoing arrows are removed. Okay, great. So that's just the backdoor criterion there.
Z prime is a subset of original covariance set Z, and nodes X and Y.
Hold up. But if we removed X, we'd still have a backdoor between X, from X to L to Y. So okay, so maybe this is an example of where P of Y is not imitable. It's not imitatable. Is that not a thing? All right. Anyway, so P of Y is imitable if there exists a set of nodes Z prime. So set of nodes Z prime must be, at least it has to include L. Otherwise, but L is latent. So I'm assuming that this is an example of of a case of where we don't have imitability.
Passes between node X and Y are blocked by that set Z prime in a subgraph where all outgoing arrows associated with X are removed. As an example, consider the driving model that we described previously. We'll assume now that the tail light does not affect the driving performance Y.
If it doesn't affect
it,
then we can.
The arrow L to Y is removed.
Then we have backdoor criterion.
Let us also remove the direct arrow X pointing to Y. We know it is verifiable that Z deseparates or blocks all the paths from node X to Y in this subgraph. That is, Z is a backdoor set. By theorem, the expert performance P of Y is thus imitable. In particular, the imitating policy is given by the conditional distribution P of X given Z, which coincides with the solution of behavior cloning using Z as a feature input set.
So they're saying that. See, this tail light thing doesn't make any sense to me, though. What is the tail light?
We will now move beyond behavior cloning and consider imitation learning opportunities where the backdoor set does not exist. Let's consider a causal diagram on the left-hand side, where X is a treatment action or transaction, and Y is reward. Here, variables X, W, and S are observed, and the covariance set Z is an empty set. And this means that there exists no subset Z prime that can satisfy the backdoor criteria. We will now show how to perform perfect imitation even when a backdoor set does not exist. The critical realization is that S is actually a surrogate point
I'm gonna say
with regard to reward Y.
it's actually so. This is actually a big thing in economics when you have these. They call them surrogate metrics. So there's some kind of yeah, I think surrogate metric is the word. There's some kind of thing that you want to optimize, and the toggle that you can turn as X, and you can't directly observe Y, so you have some kind of proxy called a surrogate. But sometimes if there's some kind of strange confounding function between X and S, you can get yourself in trouble by you think you're well, actually not in this case, but what can happen is your circuit metrics, trying to optimize the circuit can get you in trouble sometimes. I don't think that's happening here. I think that the way this DAG looks, it should be fine. So what we're saying, the S is the security probability of S given do pi. So pi is a policy that picks a value for X, equals probability of S. Why does that mean? Why is that true?
S is a surrogate in the sense that for any policy pi, if it can imitate P of S, it is also guaranteed to perfectly imitate the performance of the expert P of Y. We could thus obtain an imitating policy by solving the equation P of S given do pi equal to P of S.
So if probability of S given do pi equals probability of S, then probability of Y given do pi equals probability of Y. Imitation policy. And then here we're just integrating. All right. Let's see where he's going with this.
For binary cases, such a policy is a solution of a series of linear equations, and we show the closed form solution of pi here. Among quantities in this equation, P of S given do X is a function of the observational distribution P of X, W, S, and this formula is obtainable by using standard causal identification algorithm.
So I need to look at this one time. So I don't understand. See, this line here, I'm not really following. I guess maybe this is what the expert's doing, and maybe this is what the agent's doing. Man. And then this equality here, it just looks, I might have to dig in the paper to kind of make some header tells of these. Then we have a binary case for X, W, and S. And I sometimes I feel, especially X, so X is binary. What is W here? Some mediator. This is the kind of thing that turns off reinforcement learning researchers. They see binary examples and are like, that's I have a action space with 1,000 possible actions. Why am I looking at this? It's gotta. I feel like we're just, as the causal inference community needs to do a better job of PR sometimes. And so, and then so we have some kind of, okay, this is the front door adjustment formula. So what this is saying is that if I want to get the causal effect of X on S, given this confounding here, I can use this formula here, which is called the front door adjustment, because you're going through the front door from X, W to S, and as opposed to this unclosable backdoor. So this is something that you can derive using certain rules of causal inference. But we're taking it for granted here as a formula. And again, like this also gets to an issue of computation, which is, again, if you show this formula to somebody where W and S, S is there's many states in S, so assuming S is a surrogate, whatever. So like W and S are highly high dimensional, or they're continuous. And so how do you do? So are you going to integrate here? And what are the, how are you going to do that kind of How are you going to solve this numerically? It's a non-trivial question.
We also run simulations in the paper for this example, where x, s, and y are binary variables, and w is a digit image drawn from the MNIST dataset.
Okay, so at least we got one tensor
And our simulation results show that our causal imitation method, shown in blue,
Here's a question.
by using standard causal.
If W is an image, so what is this, a tensor? Like kind of flattened tensor of pixels? How do you integrate over that? Or sum over that? Right?
Identification algorithms. We also run simulations in the paper for this example, where x, s, and y are binary variables, and w is a digit image drawn from the MNIST dataset. And our simulation results show that our causal imitation method, shown in blue, achieves better imitation performance compared to the naive behavior cloning BC, shown in red. If you are interested in details of experiments, please check out paper and appendix. Now, in conclusion, we formulate imitation learning in the semantics of structural causal models. We also provide conditions under which imitation learning is feasible. And in the paper, you'll find a complete algorithm for finding backdoor admissible sets for behavior cloning. We also provide algorithms for finding other imitation instruments beyond behavior cloning. And you'll also find an efficient optimization procedure based on GANs for solving imitating policy in high-dimensional domains.
That's interesting.
Thank you.
To read. So these conclusions again. All right. So I mean, see, I like this. You know, one of the cool, like showing when something that people often do in a domain actually works under causal assumptions, I think is quite useful. So for example, I've seen like Bernard Shokoff has this explanation for how sometimes semi-supervised learning doesn't work under certain causal assumptions, and those causal assumptions would be actually pretty common, like pretty easy to make. So like you say, you know, for example, if I'm remembering correctly, that if the label causes the feature, then it works, and if the feature causes the label, it doesn't work. You know, that's a pretty easy thing to reason about, and save you a lot of time if you're trying to get semi-supervised learning to work and you're in a problem where it won't. So this could be something similar in the sense that it's telling you, hey, you know, here are some kind of causal assumptions you can make about your problem such that imitation learning would not work. And so the question is, you know, if those assumptions seem reasonable to you, then maybe you should question your approach. And then they give you some ways to kind of get around that. And you know, here's the paper. We're not going to get into the paper today, but it'd be interesting to see, especially with this idea of using GANs as some kind of way of solving something in a high-dimensional setting. That is, I'm kind of surprised, especially for this audience, that they didn't make that more front and center in their paper or in their talk there. There's the MNIST digits example, but yeah. So going forward, I shall. So next week, Friday at 11, I'll read another paper or we'll go through another paper, probably from NeurIPS. I like this model of like reading papers is great directly, and I've done that in a few of these streams. But actually going and looking at the pre-recorded presentations is actually pretty fun because they boil down to its essence, and then if there's a need to kind of dive deeply into the paper, you can do so. And Mondays at same time, 11 a.m., I'm live coding, working with some probabilistic modeling, live coding probabilistic modeling, and so applied probabilistic modeling. So recently I'll be going through, in the nearest term, I'll be going through some of the probabilistic programming languages that are implemented in the Julia language. I think next time I'm looking at Turing.jl. So cool. Thank you for tuning in or watching the recording, and I hope I'll see you next time.